So given a grammar, let us see how to construct an LR parsing table. Remember, to construct any LR parsing table, there are no restrictions on the grammar. Given a grammar, how do you construct an LL1 parsing table? First, ensure that the grammar is free of left recursion and should be left factored. Even if you look at operator precedence parser, given a grammar, how do you construct the parser? First, ensure that the grammar is operator grammar. But whereas if you come to LR parser, for LR parser no such restriction. Even if there is left recursion also, you need not have to eliminate left recursion, straight away you can use the grammar. Okay. So given a grammar, the general procedure for LR parsing table construction is given a grammar G, take augmented grammar. Which we call G dash. Then create canonical collection of LR0 items, LR0 items and draw DFA. Then table using DFA. We can say even reduce the DFA to table. Look at this. This is the general procedure used by all the 4 LR parsers. The only difference is in place of this, actually if it is LR0 parser or SLR1 parser, we use LR0 items, whereas look ahead LR or canonical LR uses LR1 items. This is the only difference. That means if I have to construct an SLR1 parsing table, what is the procedure? Given a grammar, take augmented grammar G dash, create canonical collection of SLR1 parsers. So I'll say LR0 items, create canonical collection of LR0 items, draw the DFA and then reduce the DFA to parsing table. If it is CLR1, then how do I modify here? Only this term has to be replaced by LR1 item. So I'll say, given a grammar for canonical LR1 parsing table construction, first take augmented grammar G dash, create canonical collection of LR1 items, draw the DFA, reduce the DFA to parsing table. Okay. So let us see how now each of this step in detail. Given a grammar, first step is take augmented grammar. What do we mean by augmented grammar? Suppose G is a grammar with some set of productions like A2 alpha, B2 beta, something like this. Okay. With S2A, something like this. S as a start symbol. To this existing grammar, you simply add one more production to change the start symbol from S to S dash. How do we change? If I included rule something like S dash to S, now this becomes my start symbol and this grammar along with this augmented, I have added a new production. Simply S was earlier my start symbol. Now I want to change the start symbol from S to S dash. So I simply added S dash to S, a unit production, just for changing the start symbol from S to S dash. Now the original grammar, the given grammar G with this augmented production S dash to S, since we have added or augmented a production along with the new grammar, we call this grammar as augmented grammar G dash. Understood? Is writing the augmented grammar is difficult? Nothing. If S is the production, simply add S dash to S. If E is the start symbol, add E dash to E. Then it becomes an augmented grammar. So, writing the augmented grammar is very easy. But what is that we are achieving by adding the truth? So, the main purpose of adding this is, this augmented production helps the parser to understand
when to stop parsing and announce successful completion. If you remember any bottom-up parser, how exactly a bottom-up parser works? Takes the input string, performs a series of reductions, detect the handle, reduce, detect the handle and reduce until it is reduced to a start symbol. So since it is performing a series of reductions, it should know when exactly, after which reduction, what is the last reduction, where it can stop and announce the successful completion. So whenever parser reduces by this augmented production, that is what is considered as successful completion. So remember the successful completion, even if you remember that parsing table, that accept token is given only when parser reduces by using the augmented production. Okay, for that sake we use this augmented production. So augmented production is to identify when to stop parsing and announce successful completion. Now let us come to the second step. This is the most important part. First we discuss with LR0 and SLR1, then we'll go to LELR1 and CLR1. That's why let me take it as only LR0 items. So what is this? We need to create canonical collection of LR0 items. So first let us understand what is LR0 items, then we'll see what is canonical collection of LR0 items.
Let us look at what is LR0 item or in simple item in compiler. Definition is very simple. Given a rule production, something like A to XYZ, an item is nothing but a grammar rule with dot at any point on the right hand side is called item. See, when you have something like this, we call it as production. But if I put a dot over here, now we call this as item. Definition is a grammar rule with dot at any point on the right hand side is a item or LR0 item. So if you take a production something like A2 XYZ, how many different items, LR0 items I can get? I can put dot at the beginning, or I can put dot after X, or I can put dot after Y, or I can put dot after Z. 4 different items I get. Okay. So definition is very simple. Once again it looks funny. Without dot we are calling it as a production, with dot we are calling it as a item. So what is the significance of dot? See, when you take a rule something like ABC, if ABC is a handle, how exactly a bottom up parser recognizes the handle and performs a reduce action? Is it going to read ABC at once? No. Reading is always symbol by symbol, one after the other, isn't it? So first it reads A. So initially when nothing is read, we say it is ABC. Dot at any point represents that how far the right hand side is seen by the parser. The dot signifies how far the right hand side is seen by the parser. For example, if ABC is the handle or the string that is to be recognized, initially when nothing is recognized, we will put the dot at the beginning. Once the parser reads A, then that is represented by the item A.BC. So A.BC indicates that, dot here indicates parser has read A, yet to read BC. Once it reads B, it is represented by AB.C. That means it has read AB, yet to read C. And once it reads C, it is shown as an item ABC. Okay. Now, dot on the right end indicates that the complete string is read, hence is ready for performing the reduce action. Okay. Actually, the items with dot at the right end is even called final items. So final item clearly shows that the entire right hand side is seen by the parser, hence ready for performing reduce action. So are you able to understand what is item or LR0 item? So once you know what is LR0 item, what we are supposed to construct is not just LR0 item, we should create the canonical collection of LR0 items. What is canonical collection? It is the set of LR0 items. Something like if C is a canonical collection, you need to create a set something like I0, I1, I2 and so on, where each of this I0 is nothing but the set of LR0 items. It is a set of LR0 items that we should create. Now let us see how do we create. To create this canonical collection of LR0 items, actually we use two functions, closure and goto. So let us understand these two functions, closure and goto. Then we'll see how we can make use of this closure and goto to construct this canonical collection of LR0 items. Let's take the simple function closure. The input for the function closure is I. I is nothing but set of items something like A2 alpha dot B beta, something like that, B2 something dot gamma, C2 dot A. So this set of items is referred as I. Given a set of LR0 items as a input to closure function, a closure function gives output also as set of items. Input is some set of items, output also will be a set of LR0 items. Let us see how this function is defined. We evaluate this function by using two rules. The first rule is very simple. Add every item from I to closure I. First rule is simply whatever you have in the input, add each of that even to the output. Okay. So with this you get some initial items. Once you have a set of initial items, what this closure function does is, in each of this set of initial items, it verifies what is the grammar symbol that follows dot. If at all in each of these items, the grammar symbol that follows dot is a terminal, then no need to add anything. If it is a terminal, no need to add anything. If at all it happens to be a non-terminal, then take the production that is defined for that non-terminal from the given grammar and add that production with a dot at the beginning, because any point of time we have to add only the items, not the production. So whenever the symbol that follows dot is a non-terminal, take the production that is defined for the non-terminal, add it to closure I by putting dot at the beginning. For example, here assume that this is the item that is there in initial I. Now if you look at the symbol that is following dot, B is a non-terminal. So what did I say? If at all you have something like this, the grammar symbol that follows dot is a terminal, no need to add anything. But if at all it is a non-terminal, we need to add items. How do we add items? For that, whenever it is a non-terminal, for every non-terminal there will be a sum rule defined in the grammar, in the given CFG. So take that rule that is defined for B. For example, assume that B2 gamma is the rule that is defined for phi. Add this to the closure I. So when you are adding to closure function, it should not be just production, it should be converted to item. How do we convert that? Just simply put dot at the beginning. That is how we convert that into item and add to closure I. Okay. So the second rule is what? If A2 alpha dot B beta is in I and B2 gamma is in given grammar, add A2 add B2 dot gamma to closure I. And remember, the second rule is a recursive rule. Repeat this until no more new items can be added. Whenever you add a new item, once again apply this rule. That means verify the grammar symbol that follows dot. Whenever it is a non-terminal, once again repeat the procedure. Okay, let's try to understand this procedure by taking a simple example. Let's take a grammar something like this. E2, E plus T or T, T2, T star F for F, F2, ID R, E. So given a grammar to construct LR parser, what is the first step? Take the augmented grammar. So what is the start symbol here? E. So to convert this into augmented grammar, I simply add E dash to E. Now let us find out closure of augmented production with dot at the beginning. E dash to dot E. So what did I said? How do we evaluate closure function? First rule is add everything from input to output. So what you have here? E dash to dot E. When you add everything from input to output, you get some initial items. Now once you get initial items, what the second rule says? Verifies the grammar symbol that follows dot. Whenever it is a terminal, ignore. Whenever it is a non-terminal, take the productions for that non-terminal from the grammar and add it with the dot at the beginning. So here E is a non-terminal. What are the rules that are defined for E? Look at this. E2, E plus T, RT. These are the two productions that are defined for E. So add it to closure I with dot at the beginning. That is how we convert a production into item. Is evaluation is over here? No. The rule is recursive. Whenever you add a new items, once again apply this rule. So when we have applied the rule for this first one, these are the newly added items. So even in the newly added items, if you observe the grammar symbol that follows dot, for example here, the grammar symbol is E. For E already we have added, so no need to add anything. Whereas here what you have is T. So because of T, what we should do? Take the rules for T, add it with dot at the beginning. So we have completed so far here. And even for the newly added items, once again verify. Whenever the grammar symbol that follows dot is a non-terminal, take the rules and add it with dot at the beginning. So here what you have is T. For T already it is added. Now for F, dot ID and dot. Now if you look at the newly added items, what you have here it is ID terminal, here it is left parenthesis terminal. So that is where it stops. This is how you get finite set of LR0 items. Now this complete set is, let us name it as set I0. I0 is the result of closure of E dash to dot E. See here in input you have only one item. But when you have applied closure function, it has resulted in how many items? 1, 2, 3, 4, 5, 6, 7. Though there is only one item in the input, when you have applied this closure function, it resulted in 7 items. 7 LR0 items, that we call it as set I0. Okay, this is closure function. Now let us look at other important function, that is goto. Coming to goto takes two arguments, I and x. I is nothing but set of items, x is a grammar symbol. So basically goto of I comma x defines what is the transition in set of items I on seeing a grammar symbol x. So this is basically defined as closure of set of all items a to alpha x dot beta such that a to alpha dot x beta is in I. What does it mean? This basically defines two steps. Find transition and apply closure. Basically this definition defines two steps. What is this? Find transition. Take the set of items I. On seeing a grammar symbol, first you find out what is the transition. Okay, so look at here, whenever you have something like A2 alpha dot x beta is in I. If the grammar symbol that is read by the parser is x, on seeing x, what should be the transition or change here? Look at this, what exactly the dot represents? Dot at any point represents what is that is seen. So here it has read alpha, on seeing x, what should be the change? This dot should be moved next to x, isn't it? So the transition here would be, the item would be now become alpha x dot beta because x is seen by the parser. Okay. So whenever you have alpha dot x beta in I, you should get set of items of the form a to alpha x dot beta, and on that you should apply closure. Once you find the transition on x as this new item. Now this is a new item. This item is different and this item is different. On this item, when x is seen, this is the new item that is generated. So on this new item, now you apply the closure, and we know the rules of closure. What closure says? Observe in this new item what is the grammar symbol that follows dot. If it is a terminal, ignore. If it is a non-terminal, add the productions with dot at the beginning. Okay, that is goto function. Let us try to understand this by taking an example. For example, I have here I naught. Let me find out what is goto of I naught on E. Remember, to find out goto at any point of time, I first two steps are to be applied: find transition, then apply closure. So let us find transition. How do we find transition? Take each item in I naught and check out what is the transition or change on seeing the grammar symbol E. Okay. For example, here if I take the first item, on seeing grammar symbol E, what should be the change? The symbol that follows dot is E and your grammar symbol is also E. When both are matching, move the dot next to E. Okay. See, look at this. Whenever this and this, the symbol that follows dot and the grammar symbol both are matching, then only we get a new item as alpha x dot beta. For example, here if my grammar symbol is something like A, then do I get any new item? I don't get any new item. It will be just an empty set. Okay. Whenever these two matches, then only I get a new item like this. So here E and E both are matching. When both are matching, the new item that will be generated here is E to E dot. Move the dot next to that E. Similarly, in the second one also, E to E dot plus T, because it is matching. Whereas in the other ones, this is not matching, 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 because grammar symbol is E. Whenever grammar symbol is not matching with the symbol next to dot, you will not get any new items. So these are the only two items we get after finding the transition. Evaluation is not complete. On this we should now apply closure. Now if you apply closure on this, here you have a final item. So when you have a final item, when you apply closure, you don't get any new items. Now whereas here the symbol that follows dot is a terminal, so no need to add anything. Now we can say this is goto of I naught on E. Let me take it as I1. Okay. Now let me find out what is goto of I1 on plus. We have seen what is goto of I1 on I naught on E. On a non-terminal we have seen. Now let us take a terminal. So this is your I naught. Grammar symbol is plus. So what will be the change on seeing plus here? Here you have a final item, so there will not be any change here. It will not produce any new item. Now whereas here it is matching. So whenever it is matching, you get a new item as E to E plus dot T. This is the result of finding the transition. Now on this, apply closure. When you apply closure, what you get? The symbol that follows dot is a non-terminal. So take the rules from the grammar. What are the rules we have? T star F or F. Add it with dot at the beginning. And is a closure evaluation is over here? It's a recursive rule. Whenever you add new items, once again apply the rule. So here already for T we have added, F is there. So for F it is ID and so this is goto of I1 on plus. Let me take it as I2. Okay. Now let me end up by taking one more example, like find out goto of I2 on T. What is goto of I2 on T? Find the transition. So T here there is a matching. So E to E plus T dot. Here also there is a matching. So T to T dot star F. No matching, no matching, no matching. Now, this is the result of transition. If you apply closure, what you have here is a final item, what you have here is a terminal, hence ends here. Let this be your I4. Got it? This is how we find closure and goto function.